Right, gentlemen, next start to week 4. Three-phase circuits. So what we're going to cover in today's session is look at different phase systems to justify largely why we use why a three-phase system is used. Going to get too heavy, do a full justification of it, but we're going to look at some of the main reasons why it's advantageous to have a three-phase system. Look at the relationship between the line and phase voltages and the line and phase currents for both a balanced star and a balanced delta three-phase system. Power in a balanced star and delta connected systems, and then looking at solving three-phase system problems mathematically. Yeah. So it builds on what we've already been doing. We'll be looking at the power, the voltages and currents in three-phase star and delta connected configurations. So first of all, it's useful to look at single-phase system, where in its simplest form we'd have inside our generator we'd have one winding, and that's from these here and here as a winding. Here's your magnet, this permanent magnet generators turning inside it one way or the other. In the position that's in on this side here, the lines, the field is cutting across these conductors as it turns, and therefore we'll have a voltage generated in that position. In this position, the magnetic field is not cutting across the conductors here and here, so we won't have any voltage induced. And then in all the positions in between these two positions, we'd have less than the maximum. So in this position, we'd have the maximum voltage induced on this side, and over here none. The generated EMF is given by that formula, basic formula there. EA-1 is BLV. That's the flux density. So B in simple terms, the strength of the magnetic field. L, length of conductor. In field, the length of the conductor. So we'd increase, we'd get a bigger voltage if we increase the magnetic flux density. We get a bigger voltage if we added more turns on the coil, so we got more length of conductor in the field. And then V is the velocity of movement. So if we spin it faster, we get more voltage out of it. Okay. The output waveform for single phase generator, if it's a maximum voltage of 20 volts, we get that kind of shape. Okay. And that's actually what we got there is a cosine wave, but it's a cosine wave and sine wave are the same shape, just shifted 90 degrees. Okay, so what we've got there is EA1, and there are some lowercase there. The instantaneous value of that is equal to 20 cos whatever this angle is along here. If we was to say RA1 was 20 sine, that would be You can draw a sine wave better than that, Michael, can't you? In there like that. Just shifted 90 degrees. Okay. So that's a single phase generator. What happens if we look at the power output from that single phase generator? So on the next page, what I've done is I've drawn a sinusoidal voltage. If we connect that generator to a load, that sinusoidal voltage would create a sinusoidal current. And here we've just got a resistor, so there's no phase shift issues at this stage. We're not worrying about that. So the current in red and the voltage blue are in phase with each other. Yeah. If we then, over that full cycle period, calculate the instantaneous value of power at all the points, that's using that formula there, what we get out is this pulsating waveform sitting on the zero power line. And there's 2 power pulses for every complete cycle of the AC mains. So we got this power that's pulsing at twice the frequency, effectively 100 Hertz. It's not a straight line, not an even power output. So what that does is it presents a pulsating load to the prime mover, the engine, the turbine, whatever's driving this generator. It's not got an even load on it all the time. It's got a pulsating load. So it's set up mechanical vibrations, making the generator noisy. Yeah. It's not smooth at all. So that's what we get power-wise out of a single-phase generator. If we go ahead and add a second winding, 90 degrees out of phase with the first one. So here's our A and B we had in the first place, there and there. And then we've put A and 1, sorry, we'll put another winding there and there. So we've got that 90 degrees out of phase with that. What we then end up with is 2 waveforms like this, 90 degrees out of phase with each other. So EA is 20 sine theta, that's the red one, and then EB is 20 sine theta plus 90 degrees. 90 degrees out of phase with it. So it's peaking 90 degrees earlier than the red one. Okay. If we then consider what the power output from that is, we got a power in A that looks like that, 2 pulses every cycle, and the power in B, 2 pulses every cycle, but shifted by 90 degrees. If we then add those in all the instantaneous values of this waveform and this waveform together, each of them peak at 200, overall we get a flat line at 200 watts. So simply adding, we get more power out of the system by simply adding a second coil 90 degrees out of phase without any increase in the size of the generator. Also, you're no longer presenting a pulsating load to the prime mover. So this inducing of vibrations in the prime mover is gone. That's just by adding one phase. So if this 20 volt 10 amp generator is giving us 200 watts and that's a flat line 200 watts into this load. Yeah. If we then go on to add a third winding, so in our 3-phase generator we've got EA coming from that one there, that's 20 sine theta here. We've got EB on those two coils there, with the distance between those being 120 degrees. Yeah. And then the third one, C, is in there. So we got B is 20 sine theta plus 120 degrees, and C, that should read there, so typo, is 20 sine theta minus 120 degrees. So we got three phases now, and each of those are 120 degrees apart. What we get now, when we add all the powers together, that green line up the top there, is all three powers added together. For adding one more winding, we get more power output. And that's still for very little or no increase in the physical size of the generator. Okay, so we've got 50% more power, 1.5 times the amount of power we had before, out of a generator the same size by adding a third winding. Now I haven't looked at it and see what the numbers do, but I would imagine if you start trying to add a fourth and a fifth, you're probably going to somewhere hit the law of diminishing returns, where you ain't going to gain that much out of doing it, and you're going to start making the physical size of the generator for a similar output that much bigger. So again, we've got this flat line, so we're presenting a steady and stable load to the prime mover, okay, and we're getting more output by adding the third winding. We also get the advantage of what we're going to be looking at in a minute, of the way we can get dual voltage systems. From one system we can get two different voltages out of it by the way we connect it up. Okay. Any questions on that so far? Gonna